Chemistry 2 time. Today we are talking about, this one is titled Thermochemistry. It is all one word. I was going to hyphenate it, which is not correct, but I just wanted you to realize that it's two separate things. Thermochemistry. What? You know what we're going to do. You already know what it is. We're going to break it up. We're going to break it down. What is thermo? To what does thermo refer? And to what does chemistry refer?
Science.
It is a science. Not only organic matter, although you're not wrong. It does pertain to that too. But the title of your text, Chemistry, Matter, and Change. So we're talking about matter and change. Matter, and we're going to put matter and its changes because that's not part of the title of the text, but matter and it, referring to matter, the changes that it undergoes. And so we're really talking about the heat changes that matter undergoes during chemical reactions. I know you have seen, but do you remember this abbreviation RXN is short for reaction? That's going to come up several times in this lesson. It's going to come up in every lesson in the rest of the year, but
I was just thinking of like good RX.
Yeah, good RX is prescription. RX is that's kind of that's actually RX. Yep, you're right. That's a different thing. Toys R Us was a different thing. She was talking about good RX, which is also a different thing. And actually, kind of interestingly, this is not part of the lesson, but does not relate almost at all. But the reason that RX is an abbreviation in medicine and especially pharmacology for prescription is because of the eye of, I think it's the eye of Horus in Egyptian mythology, which looked kind of like this. It was like that symbol. And that became, that little thing curled over. That's just a little fun fact for you. Me when I'm issuing fun facts to the students. So thermochemistry is the study of chemical reactions and the changes that take place thermally. And the most basic thermochemistry equation is, you'll remember from when you were in physical science, I'm going to do this one in pink, Q equals MC delta T. This was also your lab that we all did, the calorimetry lab. This is called the calorimetry equation. The most basic way to measure thermochemistry quantities, which is, by the way, the objective. I've been forgetting objectives all day long. Kind of like my side gig all day long has just been straight up forgetting to write down objectives. This is my third discussion of the day, which, by the way, Will, please acknowledge that I appear to be wearing a different garment. However, what has happened is I was wearing a warm garment and I took that off so I could cool down. Thank you. And actually, that's totally wrong. So let's do a different one from that, which ain't it. It is on your lab. Does anyone have their lab handy? I think I might have just marked my forehead. Did I?
It's a stop.
It's a dot. It's a beauty mark.
It honestly just looks like a pimple.
Great. That's the actual worst thing you could have said. Go on.
He exploded himself.
Yeah. It looks like a giant blackhead, like a blackhead that has no business being that big. I'm in the stance. Would someone please read the objective to me? Die. Just die. Die. Okay, what is it though? There we go. Diagram and relate thermochemistry. It is quantities. Thermochemistry. Well, you already wrote it down, right?
Yeah.
I just gave up on the word quantities. Don't even worry about it. It's too low. This shoddy cannot get low enough for that. The most basic thermochemistry quantities that we relate are these four. And by four, of course, I mean three, which is Q.
Quantity.
Nope.
Qualitative.
It's actually, joules is how we measure. I want to make sure that I get this right because I don't want to lie to you. And if I start lying, I'm never going to stop. Kind of like most of the sins that we commit, once you start, it's really hard to stop. And so I want to make sure I don't lie to you about this. I want to say that it is heat energy. It is heat energy absorbed or released. So it's heat energy measured in, as you correctly say, joules. Okay? M, you already know, is, I should have used is instead of equals there, is, what's M? You already know what it is. Yes. Measured in, the SI, in Kilograms. Kilograms or grams in this case. C is specific heat.
Yeah, I was going to guess that.
Oh, sorry, I should have let you. Specific heat, which for our equation will be kilogram.
Specific or specific?
Posta.
You're supposed to know this.
You're supposed to know this.
Well, I know, but get it because it'd be
Kilogram.
Chapisca.
It's joules per kilogram degree Celsius, or it can be joules per gram degree Celsius, or joules per kilogram Kelvin, or joules per gram Kelvin. Because we really do use either kilograms or grams depending on what quantities were given, and then we use degrees Celsius or kelvins, which remember, it's not degrees Kelvin. Kelvin is a temperature scale, it's not degrees Kelvin. The degree part of degree zero, just as another little side note to go with our, although this one actually does apply, the degree means that it starts at zero arbitrarily, like arbitrary. Have you heard the word arbitrary? It means that someone decided it starts there for no other reason than that they decided. But they arbitrarily assign zero to be the starting point, and then there can be negative or positive, whereas kelvins don't have the degree because zero is absolute zero, because Kelvin. And then delta T is
Change in temperature.
Change in temperature. Temperature, spelled correctly. And we can measure that either in degrees Celsius or in kelvins, as I was just saying. This equation, I'm going to be straight up with you, super easy. You should be able to do this you did it in your lab, or you should have done it in your lab. If you didn't do it in your lab, you easily could have done it in your lab. They're just substituting in. You had a mass of water, for instance, in your lab. You had a mass of water. Water has a specific heat that you could look up in your book right this second, and you measured how much it changed temperature. That would give you the change in heat energy. That's very easy. You just multiply them. This is freshman math. You did this when you were freshmen. The freshmen this year did it 2 weeks ago. This is freshman level math. Even if you have to manipulate, that's not difficult. Where it gets a little bit tricky is when we move on to the, and I shouldn't say tricky because it's really not that tricky, but we now, instead of talking about Q as heat energy, we start talking about enthalpy. And enthalpy, I'm going to read you the definition of enthalpy so that, again, I don't get it wrong. Don't want to have to backtrack.
Delta H.
Yeah, delta H. And we're always talking about change in enthalpy. We never know the actual enthalpy of a system. It remains a mystery. But we do measure the change in enthalpy. So enthalpy is the heat content of a system at a constant pressure. Yeah. It can relate to combustion. It can relate to melting or boiling. It can relate to all different kinds of things. But enthalpy, which is this will be change in, is change in, it's always change in heat content of a system. And we always measure this as change. We never know how much heat a thing started out with, but we can easily or fairly easily measure its change. And we have this delta H for a lot of different things. So, for instance, delta H, I don't know why I chose pink to do this entire lesson. I'm going to switch back to black. Back in black. Delta H of a reaction is equal to the change in enthalpy, or the enthalpy of the products minus the enthalpy of the reactants. Products minus the enthalpy of the reactants. So if somehow you were given those, you would be able to find the change in enthalpy. But more usually, we would measure the change in enthalpy for a given reaction. What again does the term reaction or RXN stand for? I already just told you, it's reaction. So endothermic processes, delta H greater than 0 is endothermic. Delta H less than 0 is exothermic. This is important for you to just memorize. We're going to talk about it conceptually, but you should probably just have it memorized. So basically, if the numbers are positive, how has the energy changed in that reaction? It's endothermic, meaning that reaction did what to the energy of its surroundings?
It heated it up.
Wrong. Opposite of right.
Cooled it.
It absorbed heat from its environment, which made it, if you were to touch it, it would feel cold because it would be absorbing heat. Remember, maybe you don't remember, but I will remind you that what your body feels as hot or cold is actually, much like what we just talked about, where we never actually talk about enthalpy, we're talking about change in enthalpy. What your body feels as heat or cold is actually heat energy entering or leaving your body. So conveniently, someone gave you a little bit of warm tea. If you feel the tea as warmth, do you feel? Maybe you don't because yours is well insulated. Mine's gone. Yours is in your tummy. If you put your finger, don't put yours in because yours is in your tummy. But if you did put your finger in your tea, it would feel warm because the heat energy is flowing into your body. What your body perceives as warmth is actually the flow of heat into your body. What your body perceives as cold is actually the flow of heat energy out of your body. Okay? Does that kind of make sense? Here's the...
Really, there is no hot or cold.
Your body doesn't actually detect temperature straight up. It detects change in temperature, or it detects heat, influx and outflux. So if you touch, okay.
Whiteboard.
No, don't touch shoddy because that has its own temperature. Everything in this room is approximately 71 degrees Fahrenheit.
Not us, though.
Not us, you're right. Everything in this room besides the human beings, like if you were to look at this in infrared camera, you would see that everything in this room is approximately 71 degrees Fahrenheit. But if you touch chair leg, do it now. Find a chair leg and touch it. Touch. It feels cold. If you touch, let's say, book bag or something else that isn't on your person but is soft, it feels warmer. It is not. They are the same temperature. They're both 71, but because the chair leg is a better conductor, the heat energy can leave faster and your body detects that as feeling cold. It is not. And this, your body does not, it doesn't leave as fast, and so your body does not detect that as cold. So if a chemical reaction is is gaining energy from its environment, that to you, that reaction would feel cold because it's endothermic. And similarly, if it's exothermic, it's releasing its own heat, that reaction would probably feel warm to you. And sometimes people get thrown off by these signs, but basically this one ends up being positive is endothermic and negative is exothermic. Okay, so memorize that for change in enthalpy, positive means endothermic and negative means exothermic. We good?
Yeah.
And this is true not just for reactions, but this is also true for things like enthalpy of fusion, which is melting, enthalpy of vaporization, which is boiling. But there are lots of different kinds of enthalpy, and it applies in a similar way. It's always final minus initial, because that's how we calculate delta anything. And they're always going to be positive or negative depending on whether energy is released. Sorry, let me say it in the right order. Whether energy is absorbed or released in that order. Okay? Do you have questions about enthalpy in general? This is kind of conceptual. You don't need a lot of math with actually this equation, but does that make sense to you how we use enthalpy? You can think of it like heat, but remember it's actually a proxy for changing the heat content of a system. So, what we actually do with it, you might ask yourself, what do we actually do with it? If this is not the thing, what we actually mostly do with it is this idea of Hess's law, named after a guy, lady, a person, Hess. I want to find out who.
I thought Hess was the last name.
Yes, but of who? The book doesn't tell me.
Jeremy.
Bonus points if you look up person Hess. Jeremy, perhaps. Jenny. Could be Jenny. You really don't know, or at least not from the book. If you look up who was Hess, I will give you bonus points. But Hess's law states, Hess's law we can think of as you basically add them together, but I want to read to you what the book says. Hess's law states that if you can add two or more thermochemical equations to produce a final equation, the sum of the enthalpy changes for the individual reactions is the enthalpy change for the final reactions. So you can, let's phrase this a little more professionally than you can. Component reactions, enthalpies, can be added to find a resultant reactions enthalpy. Okay, we're gonna break this down in a second, and I'm not gonna break it down for nothing, as Andre 3000 says. Let's start with breaking this down. What's the word component mean? Write these down if you don't know. I'm not gonna write them because I do know, but if you don't know what these mean, you might consider writing them. What's the component mean?
What's that cycle? Add to find a what?
Resultant reactions enthalpy. What's the word component mean? Maybe if I ask you this question, what are the components of that pencil sharpener?
Gears.
It's got gears. What else?
Sharpeners.
Electric.
Sharpeners. It's got some electricity running around in there. Wires probably. But you understand, if I ask you what a thing's components are, you can tell me. So what does the word component mean?
Things added up to make.
Okay, good. Yeah. Things added up. So the reactions that make up this other reaction, that's what a resultant is. So the resultant is what results from all those being added up. So the components add together to make the resultant. Those are kind of common terms that we use in a lot of different fields, but I'm aware of them happening in both this and in physics. So components add together to make a resultant. And then, of course, we have these reactions. And so if we know, let me give you an example from the book. If we know that two equations added together could make another equation, we can just add up the enthalpies of those equations. So, for instance, if we are analyzing as the resultant equation, this one, is this visible on screen if I write over here, or should I put it somewhere else? It's not visible on screen. How low can I go? Can I go down low? Is that good? Okay, H2O2 yields H2O plus O2. This is not balanced. If this is the resultant equation that we're talking about, and we also know these other two equations, H2 plus O2 yields 2H2O. Oops, sorry, I don't want to put balanced in there. And H2 plus O2 yields H2O2. You can see how these could be thought of as components of this one. Do you see how they have similar things? This one's got hydrogen and oxygen. This one's got oxygen here. This one's got water. There's water here. This one's got hydrogen and oxygen. As we already said, there's oxygen here. And this one's got hydrogen peroxide. You see how this equation can be thought of as being made up of these two equations. You see how they relate? Like if we squish these together, we can squiggle them around a little bit, which is part of Hess's law.
Like Tom Riddle, Lord Voldemort.
Yes, exactly like. Thank you for relating it to the young people of 2001 who are very interested in. Can I write over here?
Erase the pink. It's not necessary.
Tom Marlvolo, is that something like, right?
Yep.
Riddle is an anagram of,
Lord.
I think it's actually I am Lord Voldemort. He checked it himself just to prepare for this lesson. But see, we can squizzle these around much like that. Very good analogy. If we flip this one, we could, oh, that's not the right one, sorry. Pretend I didn't. Pretend that ain't me. If we flip this one, now we have the hydrogen peroxide on the right side, and you can see that these H2s will reduce out, and the whole thing, we're going to kind of do it conceptually, but we can easily make it so that the parts of this that we don't need, the parts of these that we don't need reduce out, and that the things are located on the correct sides. And all we have to do, this is Hess's law, and you'll have practice with this. We're not going to do it on the board, but we will have practice. All you have to do is, for whatever the enthalpy you're given for these, which I didn't write because they're not balanced, whatever the enthalpy there is, if you flip them, let me write this down for you. If you flip them, I'm going to write the word flip them, change the sign. Flim. I just wrote phlegm. Me when I write phlegm. Flip. If you flip them, that changes the sign. And then as an example, if you double them, what do you think that does to the change in enthalpy? It just doubles it. I'll change the sign of delta H. So these would be given to you with a delta H. Let me show you the example in the book. For if you're watching this in the future, you don't have access to your chemistry book, which I assume you will do. You can pause it. You're given delta H's. If you flip one of these equations to make it add up to the right one, you would change the sign. So if it was positive, you make it negative, and vice versa. If you do anything multiplicative with it, like balancing it, you would just double or multiply by 3 or whatever. And then, very simply, the process itself is a little complicated, but very simply, all we do with what results of these delta H's is you just add them together. That's what Hess's law is. we can add those delta H's together after we squiggle them around, like Tom Marlborough Riddle. We add those together, and that gives us the delta H of this one. So we come into the problem not knowing delta H for her. We squiggle these around. Whatever we do to them, we have to do the delta H, and then we just add the delta H's together. And it really is that simple. It gets a little bit more complicated when you're actually doing the math because you have to do things like multiply 188 by 2, which calculators will help you with that. And then you have to add negative 572 and 376. But that math becomes easy once you understand what's going on. So I would say the main math job for the chapter is this Hess's law. And you're going to be like, dog, this is hard. But if you just remember that I told you it's easy, you'll realize that I'm right. Lastly, and this one is we only really do this one conceptually, the Gibbs free energy equation. Where will we even put that? We'll do it in green, and I will give it to you over here. Gibbs free energy, delta G. Wow, that's totally illegible. Delta G equals delta H minus T delta S, where delta G is Gibbs free energy. Delta H we already talked about, T we already talked about, and delta S is entropy. Entropy you can think of as the number of different ways that a system could be arranged. It's kind of thought of as a measurement of disorder of a system. These values will be given to you. As far as I know, this is a plug and chug problem in your book, but you should be aware that if delta G is positive, it's not spontaneous, and if delta G is negative, it is spontaneous. So negative delta G means the reaction is spontaneous, which means that it will occur. You know what spontaneous means, right? If you're, who do you have in your life? If your best friend, Cody Holmgren, is spontaneous, that means he just does things. He doesn't say, hey, let's plan in 3 weeks to go to the bowling alley. You just get into his car and he's like, we're going to the bowling alley. That's spontaneous. I don't know if that's actually true for him. But for a reaction, it's the same thing. A reaction that is spontaneous happens on its own without added energy. A reaction that is not spontaneous does not happen unless energy is added to it. Not never, and it's statistical, but it's unlikely to happen on its own. I think that pretty much covers it. There's another thing I need to stop saying. I've been trying all day not to say that. But there is a type of Hess's law where you use enthalpies of formation instead of actually given equations, but those are all found in the reference materials at the back of your book, and when you get to those, let me know and we'll work on them together. Do you guys have questions?
No.
Four kinds of
no.
4 kinds of math.
4 kinds of chat?
4 kinds of math chat. In the 4 kinds of math we have are calorimetry, which you should remember from being a freshman, Hess's law, including enthalpies of formation, that's 2 kinds, and then reaction spontaneity.
What's that second delta G? The first delta G.
Delta G is Gibbs free energy. It's again named after, I think, Gibbs.